Hello, my name is Glenn Lipscomb. I'm a professor in the Chemical Engineering Department at the University of Toledo. It's a pleasure to give this talk entitled Novel Assembly of Charged Mosaic Membranes for Salt Separation from Aqueous Solutions. The work you're going to see here is primarily that of Giselle Basigi. She was a PhD student until about a year or so ago, and she currently is working at Compact Membrane Systems. I'm sure you're familiar with the concept of an ion exchange membrane. What's illustrated here on the top is a cation exchange membrane, and on the bottom an anion exchange membrane. What makes these materials unique is that they selectively transport one ion or the other. For instance, the cation exchange membrane allows selective transport of cations across it, whereas the anion exchange membrane allows selective transport of anions across it. This selective transport is enabled by having charges distributed along the backbone of the polymer that makes up the membrane. In the cation exchange membrane case, these are negative charges. They're balanced by a cation that is mobile and then therefore can be transported across the membrane. These membranes, when used, will allow transport only if the counterion is also transported at the same time. Now, this could be done in electrodialysis or reverse electrodialysis by alternating these membranes in a stack. Charged mosaic membranes get around the need for having membranes in a stack by trying to bring together the cation exchange regions and the anion exchange regions in close proximity, such that when a salt ion approaches, such as sodium chloride, the salt ion can dissociate into sodium and chloride, and the sodium can transport through the cation exchange membrane and the chloride through the anion, and after transport they recombine to form the salt in the solution. This type of membrane has the potential to selectively remove salt from seawater or brackish water and therefore desalinate the water. This is in stark contrast to reverse osmosis processes, which remove the water from the salt. There's been a great interest in charged mosaic membranes dating back to the early 1930s with Solner. People have tried numerous different configurations. They tried embedding resins into tried embedding cation and anion exchange resins into a matrix, such as you see here in this diagram. On the right-hand side, in the upper left part of it, people have also tried to construct block copolymers in which alternating regions are cation and anion exchange materials. And finally, people have tried stacking ion exchange resins together and forming a very, and then reducing the thickness of the stack through extrusion. Despite all the past work, there's still not a good material for use as a charged mosaic membrane. And so what we sought to do is come up with a new way to make these membranes that might lead to improved performance, greater salt enrichment, higher hydraulic permeability, while maintaining physical stability. We also wanted to have a way to predict the performance of these materials, a simple way. Our initial idea was to take nanofibers, such as titanium, and then to coat them successively with layers of a polyionic material, a polyelectrolyte. So as you see in the figure down here, starting with a nanofiber, what we would do is coat on the surface of that positively charged nanofiber a polyanion, and then remove that from the solution containing the polyanion, and then immerse it into a solution containing the polycation to form a two-layer structure, and then repeating this to form subsequent layers. By doing this, we had hoped to form what you see here over on the right, which is a concentric layered structure in which we have alternating layers of cation and anion exchange materials. And these would then form the pathways for transport in a charged mosaic membrane. To use these fibers, we'd have to embed them in a porous support. And the initial idea was that we would just present a solution of these fibers onto the membrane and force the liquid through the pores of the fiber and hope that the fibers would embed into the pores. Well, we were successful in coating the nanofibers. On the top here you see TEMs for 2 bilayers and for 4 bilayer coatings. And on the bottom you see these membranes on the surface of a porous membrane in which we tried to impregnate the fibers. And you can see over here on the lower right is that some of the fibers did enter into the pores, but there's many more that deposited on the surface, as you see here on the lower left. We tried to study these materials for their ability to selectively transport salt and thereby desalinate a feed solution. We started off using polysodium sulfonate, PSS, as our cation exchange material. And we also use polyallylamine hydrochloride as our anion exchange material. And then we use these with different salt solutions. What you see here in the picture is the picture shows our small cell that we use for doing the testing. These are the preliminary results that we had, and if you look at the top two figures, they show the enrichment that we saw with these two different fiber coatings, with the 2 bilayer and the 4 bilayer. The bilayer is referring to a layer of cation and anion polymer. And what we see is that we had very small, if any, measurable enrichment. And the reason for this is that the fibers didn't really enter into the pores of the fiber. They deposited primarily onto the surface, as you can see in the SEMs down here below. Due to the difficulties we were having with the nanofibers, we decided to pursue a different approach to forming the charged mosaic membranes. We thought we could assemble the membrane by having the polyelectrolyte deposit within the pores of a porous support. And we were using a combination of diffusion and convective flow in order to create the charged mosaic structure. First, we take a porous support, and then we coat the surface of that support with, in this case, the polystyrene sulfonate. After coating it, we let the polymer, the polyanionic material, diffuse into the pores of the membrane. Before, we coat the surface of the membrane with the polyallylamine hydrochloride. In this case, we force the solution through the pores in order to create what we call a first bilayer within the pores of the membrane. The intent of depositing the polyanionic and polycationic polymers into the membrane pore was to create a structure such as that you see here. This is a cross-section of pore looking from top to bottom, in which we have ionically cross-linked polymers. But the cross-linking leaves free many different charge sites along both polymers, and it's these charge sites that we were hoping would lend the charged mosaic character to it, that would allow a salt ion to dissociate and then diffuse or move by convection through the pore of the membrane from site to site within the charged mosaic structure. To confirm that we're able to form this membrane within the pores of the support, we did SEM EDS. And what you see here in the center picture is a subtraction of the image on the left from the image on the right, showing the location of sulfur, which is a sign of the presence of the PSS within the structure. So we feel comfortable performing the structure. To enhance the potential for removing salt selectively and concentrating it with the charged mosaic structure, we decided to add polystyrene sulfonate to the feed salt solution to superimpose a Donnan equilibrium effect on top of the charged mosaic structure. What you see here is, for the initial testing that we did, the 3 different feed solutions that we used, in which we changed the salt concentration and the concentration of the polyanionic polystyrene sulfonate. What's shown here is a salt enrichment that was achieved with the initial test that we performed, using up to 6 different layers in the membrane structure and using the 3 different feed solutions. What's plotted on the y-axis here is the salt enrichment. That's the difference between the salt concentration in the permeate and the salt concentration in the feed divided by the salt concentration in the feed. And then on the x-axis, of course, is the 3 different solutions that we use, the 300, 600, and 1200 part per million salt. Now the polystyrene sulfonate, the PSS, was added to this such that the ratio of the moles of sodium from the salt, from the sodium chloride, was equal to the moles of sodium that came along with the polymer. So we had equal molar amounts of sodium from the 2 components in the feed. Now what's shown here is the 6 different layers. What these represent, the 2 layer represents the initial combination of a polystyrene sulfonate, the PSS, and the PAH layer membrane. And then on top of that was added a PSS to form the 3. And then we had a PSS, PAH, PSS, PAH in order to get the 4, and etc. to get up to 6. What you see is that as you increase the number of layers in the membrane, is that we get an increase in the enrichment, an increase in the concentration of the permeate. The conditions under which we were running this membrane was around up to about 45 psi pressure difference across the membrane in order to drive permeate. What we see is that as we went up to about 4 layers, there was an increase in the enrichment, and after 4, we saw a drop, and eventually, in some cases, what we saw was a rejection of the salt. We feel in the cases where we saw rejection is that we had sufficiently high number of layers, is that we did not have free sites that would allow the charged mosaic structure to exist, and therefore we were rejecting the salt transport across the membrane. To try to provide a theoretical basis for the experimental observations, we turned to the extended Nernst-Planck equation to describe transport across the membrane, and also equated the chemical potential of the salt ions at the interface between the membrane and the contacting solution in order to calculate the concentration of the salt in the membrane. Doing this, what we find is that the concentration of a salt, such as sodium chloride in the membrane, can be increased above the concentration of that same salt in the contacting solution by the presence of a polymer, a polyelectrolyte, that physically is excluded from the membrane, excluded from the pore structure, but contributes one of the two ions of the salt to the contacting feed solution. So for instance, if we had polystyrene sulfonate, we could be contributing additional sodium into the feed solution from the presence of that polymer. And that contribution leads to an increase then of the sodium inside the membrane, according to this expression right here, which is counterbalanced by chloride to lead to an increase in the salt concentration in the membrane relative to the salt concentration that's in the contacting solution. While the salt flux across the membrane can contain both a diffusive and a convective contribution, what we have found is that the convective contribution seems to be dominant. And then finally, we can calculate the enrichment of the salt, the concentration of the salt in the permeate relative to that in the feed from the expression that you see there. What's shown here is plots of enrichment versus salt concentration for a 2-layer in the upper left and a 4-layer in the upper right and a 6-layer membrane in the lower left. The enrichment measured experimentally with the blue squares, and then the theoretical prediction based upon the Donnan equilibrium, which is the unfilled red triangles. What you can see is there's a big difference between the two in all cases. To try to account for a potential cause of this, what we decided was to assume a fraction of the free salt inside the membrane is not mobile, that this salt is split, that the anion and the cation are associated with the polymer that makes up the membrane structure, and therefore are not able to diffuse freely or to convect freely. So what we did is we estimated that portion of the salt that's in the membrane that is unable to move freely, that is tied up with the membrane structure itself, by looking at the very first point, the enrichment point that we measured experimentally, and comparing it to what we predicted theoretically with no immobilization. We determined the amount of immobilization that would be needed in order to bring that first point in agreement with the experimental data. So for instance, for the 2-layer membrane, in order to bring the predicted enrichment from 40% down to the experimental value, which is around 10%, we had to subtract off a certain amount of salt concentration in the membrane, which is given by the value of C in the title for that chart there. Doing that does bring the points closer, but you can see that as you increase the salt concentration, is that the predicted enrichment, according to the Donnan equilibrium, continues to increase, while the experimental enrichment tends to decrease, and that's true in all cases. If you compare the 2 and the 4 and the 6-layer membranes, what you see is the 4-layer membrane gave the highest overall enrichment experimentally and had the least variation with the salt concentration in the feed solution, as shown here. Finally, if you look down the lower right-hand corner here, you see what was the amount of immobilized salt that was subtracted off in order to, as a function of the number of layers in the membrane, in order to bring the predicted enrichment in line with the experimental values. So you can see that this amount decreased as we increased the number of layers, and then it increased after we get past about 4 layers. And this is where we seem to find the optimum performance is right here, about 4 layers. Now, to explain the difference that we were seeing between the predicted enrichment and the experimental enrichment, the higher salt concentrations, there's 2 possibilities that we propose. One is that there's concentration polarization that exists, so that the bulk concentration is not indicative of what the concentration is at the surface of the membrane. And this can be concentration polarization related to the polymer itself or related to the dissolved salt. Another factor is that the membrane that is present inside here, the structure of that membrane, may change depending upon the salt concentration, the free salt concentration in the membrane itself, and thereby change the amount of fixed salt that's associated with the membrane. What's shown here is a couple plots looking at the effect of changing the feed concentration, and in particular, up in the upper left side, what's shown here is the effect of changing the salt concentration for a high level of polymer concentration. And so for the range of salt concentrations that you see here, from on the order of 100 to 500 ppm up to about 6,000, what we see is that the ratio of sodium contributed from the polymer in the feed solution relative to that contributed by the dissolved salt changes from about 20 to about 1. 20 to 1 to 1 to 1. And as we change the dissolved salt concentration over this range, and thereby change the ratio of the sodium contributed by the polymer to the sodium contributed by the salt, we see a change in the enrichment from nearly 200%, where we have 20 to 1 ratio, down to something that's on the order of 15%, we have 1 to 1. If we estimate the amount of fixed salt that's present in the membrane, of immobile salt that's present in the membrane, due to the structure of the membrane, from the point at the 20 to 1 ratio, we end up with a value here that you see here. If we subtract that off and redo the calculate then what we expect the enrichment to be, we get the red diamonds right here, red triangles that is, and what you see is that we get reasonably good agreement between that prediction, that very simple prediction, and the experimental data. What's shown here is the hydraulic permeability of the membrane as a function of time for a 1-layer membrane up to a 6-layer membrane. What we see is that the membranes remain relatively stable. All the membranes remain relatively stable in terms of their hydraulic permeability. The chart down here the table down here at the bottom compares the hydraulic permeability of the 4-layer membrane to that of a nanofiltration and RO membrane. You can see that the hydraulic permeabilities of these membranes are significantly higher, up to a factor of 10. Here we look at an even broader range of the ratio of sodium contributed from the polymer to the sodium contributed from the dissolved salt, in order to see how much we could increase the enhancement that we could get in the salt concentration in the permeate. Here, that ratio, instead of going from 0 to 20, goes up to nearly 100. And we did this by varying the concentration of the polymer from 25 grams per liter up to 125 grams per liter. What you can see is that at a ratio of 100, we're able to get enrichments that are nearly 800%. What's also shown here, in addition to the experimental data, the blue squares is the red-filled triangles indicating the calculated values from Donnan equilibrium. And we estimated the amount of salt that was fixed within the membrane structure for the lowest ratio of the sodium contributed from the polymer to that contributed from the dissolved salt. We see we get very good agreement here between the predicted enrichments and the experimentally observed enrichments. If we're using this membrane and using a Donnan equilibrium in order to produce drinking water, one of the concerns is what is the impact of having polymer enter into our produced water, into our drinking water. So in order to overcome this concern, we looked at using food-grade polyelectrolytes instead of styrene sulfonate and the polyallylamine hydrochloride. Here we're using sodium alginate and polylysine hydrochloride in order to form the membrane and also in order to form the feed. We take salt, the 3 feeds that you see here, we dissolve sodium chloride with a certain amount of the sodium alginate in order to control the ratio of the sodium contributed from the polymer to that contributed from the salt, the dissolved salt. The chart down here shows you the enrichments that were possible as a function of the salt concentration, the dissolved sodium chloride concentration in the feed. What we see is that with these food-grade polymers, we're able to achieve comparable enrichments in excess of 100% at the lower salt concentrations. Now the predicted values here, in which we take into account the amount of fixed sodium chloride that's present in the membrane due to the membrane structure, they also agree fairly well with experimental values. We also examined the long-term stability of these. Long-term is a relative word here because we only went up to about 10,000 seconds, but over the time frame that we did these experiments, we saw using the food-grade polymers comparable stability to that using the PSS and the PAH. Down here in the table, you also see a comparison of the hydraulic permeability from the PSS-PAH membrane, and that from the food-grade polymer, the polylysine, and the sodium alginate. You see we have comparable values for the hydraulic permeability. So in conclusion, I'd just like to state that we believe we have demonstrated the feasibility and reliability of a new type of charged mosaic membrane, which in combination with using the Donnan effect to increase the salt concentration in the membrane, we're able to produce a permeate that is enriched in the salt in the feed and thereby extract the salt. It has certain advantages, this membrane, that in terms of formation time and ease of preparation. What we found is that having a 4-layer membrane gave us the optimal performance. The enrichment that we saw in the salt in the permeate increased as the polymer to salt concentration. The polymer to salt concentration ratio increases. That this increased the Donnan equilibrium concentration in the membrane and thereby the performance. We have flexible polyelectrolyte choices. We can use food-grade polymers, and we can also vary which polymer we use as the Donnan driving polymer. We used PSS in the results that you see here, but we've also looked at using the PAH and ended up with similar results. Finally, results are not shown here, we're able to demonstrate an enhancement in the enrichment upon cross-linking. The process we described thus far is capable of removing salt from a saline solution, but what's left behind is a solution of the polymer that we use to help drive the Donnan equilibrium and salt removal and the drinking water that we wish to recover. So a secondary step is needed to remove the polymer and recycle it for use in the Donnan equilibrium charged mosaic step. What's shown here is a 2-step process that would allow that to happen. Our saline feed that we wish to desalinate, say a brackish water feed, is fed to the Donnan equilibrium membrane here stage. Salt is removed to produce a concentrated brackish water, which is rejected then. The solution that leaves here has had salt removed, but still has a polymer in it, which we would like to remove. We send that to an ultrafiltration step, then we can remove the polymer with very high efficiency and produce then the reduced sodium chloride brackish water stream that would ultimately be potentially our drinking water if we were to do this in a multi-stage process. The polymer that we've removed, we can recycle back in and mix that then with a portion of the brackish water that we recycle back as well into the charged mosaic membrane unit here. What this does, it gives us a continuous process in which we take brackish water feed, produce a concentrated brackish water reject, and then a drinking water here, which has, if we choose the ultrafiltration step properly, we'll have a minimal amount of the polymer in it that we're using to drive the process. Ideally, none of it. And with that, thank you for your time. I look forward to hearing your questions.